At a certain moment 13.8 billion years ago, nothing existed. No space, no time, no matter, not even the concept of nothingness itself. Then, within a point smaller than an atomic nucleus by countless orders of magnitude, the entire universe suddenly exploded into being. This was not an explosion that occurred somewhere, this was the birth of space and time itself. Everything we know about reality is built upon this seemingly absurd premise. But this is not even the most shocking part. The most disturbing truth is that we can actually trace back to that instant, that we can use mathematics and physics to reconstruct that moment of creation. We not only know how the universe began, we even know what happened in the first billionth of a second after its birth. This cognitive ability itself is a miracle, an intelligent life form produced by the Big Bang actually capable of understanding its own origins. Big Bang theory tells us that the entire observable universe, containing hundreds of billions of galaxies, each containing hundreds of billions of stars, was once compressed into a space smaller than a proton. At that inconceivable density and temperature, the physical laws we know completely break down. No atoms, no molecules, not even fundamental particles. Only pure energy, existing in a form we cannot imagine. Then, after Planck time, 10 to the power of negative 43 seconds, the universe began its initial and most violent expansion. This was not the movement of matter through space, but the creation and stretching of space itself. Imagine this. If you could expand a pinhead-sized region to larger than the solar system within 1 second, you would get a slight sense of the violence of that moment. But even this analogy vastly underestimates the true scale of cosmic inflation. Between 10 to the power of negative 36 and 10 to the power of negative 32 seconds, the universe's size increased by at least 10 to the power of 26 times. Let us use more concrete analogies to understand this terrifying scale. If you held a bacteria-sized object during cosmic inflation, it would expand to larger than the entire observable universe. If you had an atomic nucleus, it would instantly become a giant sphere with a diameter exceeding 1 light-year. This expansion speed far exceeded the speed of light, not because matter was moving, but because space itself was being created at superluminal speeds. Even more dizzying is the time scale. The universe's entire early history, from quantum fluctuations to the birth of the first stars, occurred within a time span that, compared to human history, is as insignificant as human history is compared to the age of the universe. In the first second after the universe's birth, more change occurred than in Earth's 4.5 billion year history. In that 1 second, the universe expanded from a point smaller than an atom to a space with a diameter exceeding light years, temperature dropped from infinity to 1 billion Kelvin, fundamental particles began forming, and fundamental forces began differentiating. But perhaps the most unsettling realization is that everything we see now, every star, every galaxy, every life form, is a direct consequence of that initial moment. Every atom in your body carries the imprint of that creative moment 13.8 billion years ago. In a sense, we are not merely observers of the universe, we are the universe itself, tools created by the universe to understand itself. In the universe's initial moment, the temperature was unimaginably high, exceeding 10 to the power of 32 Kelvin. At such temperatures, even the most fundamental particles could not exist stably. The boundary between energy and matter completely disappeared, and the entire universe was an ocean of plasma composed of pure energy. But as the universe expanded, this primordial fireball began cooling, and what physicists call symmetry breaking processes began to occur. At 10 to the power of negative 11 seconds after the universe's birth, the temperature dropped enough to allow W and Z bosons to exist stably. This marked the separation of electromagnetic and weak nuclear forces. Before this, these two forces were unified. This seemingly technical detail actually has profound significance. If this separation had not occurred, or had occurred slightly differently, the chemical reactions we know would be impossible, and life would be out of the question. Immediately after, at 10 to the power of -6 seconds, the strong nuclear force separated from the other forces. This moment marked when quarks began combining into protons and neutrons, the basic components that constitute all atomic nuclei we see today. But this process was not peaceful. During quark confinement, the universe underwent a violent phase transition, like water suddenly freezing. This phase transition released enormous energy, further heating the universe while also determining the final ratio of protons to neutrons. When the universe reached 1 second old, the temperature had dropped to 10 billion Kelvin, still 1,000 times hotter than the Sun's core, but cool enough to allow neutrinos to decouple from other matter. Before this, neutrinos existed in thermal equilibrium with photons, electrons, and other particles. But when the temperature dropped to a certain level, neutrinos suddenly became almost non-interacting with other matter. These relic neutrinos still fill the entire universe today, serving as direct evidence of the universe's early state. However, the truly dramatic moment occurred in the first 20 minutes after the universe's birth. This process, called Big Bang nucleosynthesis, determined the abundance ratios of light elements in the universe. When the temperature dropped to 1 billion Kelvin, protons and neutrons began combining to form deuterium nuclei, the nuclei of heavy hydrogen. But this process was extremely fragile. If the temperature were slightly higher, deuterium nuclei would be dissociated by high-energy photons. If slightly lower, protons and neutrons would lack sufficient energy to overcome their mutual charge repulsion. Within this narrow temperature window, a universe-scale nuclear reaction began. Deuterium nuclei combined with protons to form helium-3, and helium-3 combined with neutrons to form helium-4. In just 20 minutes, approximately 25% of the universe's protons were converted into helium-4 nuclei. This ratio was crucial. If helium abundance were higher, the properties of first-generation stars would be completely different. If helium abundance were lower, nuclear fusion processes within stellar interiors could not proceed effectively. But Big Bang nucleosynthesis also had its limitations. Due to the absence of stable atomic nuclei with mass numbers 5 and 8, this process could not produce elements heavier than helium. Lithium-7 was the only heavier element that could be produced in significant quantities, but its abundance was also extremely small. This meant that for the universe's first 380 million years, the entire universe consisted almost entirely of hydrogen and helium. No carbon, no oxygen, no silicon, no iron, all these heavy elements that constitute planets and life did not yet exist. When Big Bang nucleosynthesis ended, the universe entered a relatively quiet period. Temperature continued dropping, but no major physical processes occurred. The universe continued expanding, density continued decreasing, but the basic composition remained unchanged, approximately 75% hydrogen, 25% helium, and trace amounts of lithium. This period is called the radiation-dominated era, because the universe's energy density was primarily contributed by photons. However, beneath this apparent calm, a more profound process was underway. The universe contained tiny density fluctuations. Certain regions had matter density slightly higher than average, others slightly lower. These fluctuations were extremely small, only 1 part in a million relative difference, but they would determine the universe's ultimate fate. In regions with slightly higher density, gravity began gaining the upper hand, attracting surrounding matter. In regions with slightly lower density, matter was repelled elsewhere. The origin of these density fluctuations remains one of cosmology's major mysteries today. The most widely accepted theory suggests they originated from quantum fluctuations during cosmic inflation. At that extremely microscopic scale, Heisenberg's uncertainty principle caused random fluctuations in energy density. When the universe inflated, these quantum-scale fluctuations were stretched to macroscopic scales, becoming the seeds for later galaxy and galaxy cluster formation. This explanation, while mathematically perfect, is philosophically disturbing. It implies that the large-scale structure of the universe we see today, the distribution of galaxies, the arrangement of galaxy clusters, even the existence of our Milky Way, all originated from the randomness of the quantum world. In other words, the universe's fate was determined by the uncertainty principle. If quantum fluctuations had been slightly different, our galaxy might not exist, Earth would not have been born, and we would not be here contemplating these questions. But even with these density fluctuations, the early universe was still a relatively uniform place. Matter and radiation were tightly coupled, forming a vast plasma. Photons could not propagate freely because they would immediately be scattered by free electrons. The universe was opaque, filled with a dense, hot plasma similar to the Sun's interior. This state persisted for approximately 380,000 years, until the universe cooled enough for electrons to combine with protons to form neutral hydrogen atoms. This process is called recombination, though the name is somewhat misleading. This was actually the first time neutral atoms formed in the universe's history. When recombination occurred, free electrons suddenly disappeared, and photons gained the ability to propagate freely. The universe transformed from opaque to transparent, and there was truly light for the first time. The light released by recombination still fills the entire universe today. This is the cosmic microwave background radiation we observe. These photons carry detailed information from when the universe was 380,000 years old, tiny temperature variations, subtle density differences, even traces of sound waves propagating through the early universe's plasma. By analyzing these ancient photons, we can reconstruct the universe's early history, just as archaeologists reconstruct ancient civilizations through ancient artifacts. But recombination also marked the universe's entry into a darker period. Although the universe became transparent, there were no stars yet to illuminate it. Hydrogen and helium gas began gathering under gravity's influence, but the gathering process was extremely slow. Without heavy elements to help gas cool, without dust particles to serve as condensation nuclei, early gas clouds found it difficult to reach the densities required for star formation. This period is called the Cosmic Dark Ages by astrophysicists. For several 100 million years after recombination, there were no light sources in the universe. The only light was the cosmic microwave background radiation, but as the universe expanded, these photons' wavelengths were stretched and their energy continuously decreased. The universe became colder and darker. However, within this apparent silence, gravity was doing its work. Those tiny density fluctuations began growing, dense regions became denser, and sparse regions became sparser. Initially, this process proceeded slowly because radiation pressure was still strong, hindering matter's aggregation. But as the universe cooled, matter began dominating the universe's energy density, and gravity's effects became more significant. In this process, dark matter played a crucial role. Unlike ordinary matter, dark matter does not interact with photons and thus is not affected by radiation pressure. Before recombination, dark matter had already begun clustering, forming a complex web-like structure. When ordinary matter finally freed itself from radiation's constraints, it found that dark matter had already prepared a scaffolding, a cosmic network composed of dark matter halos. Ordinary matter began gathering along these dark matter structures, forming the first gas clouds. These clouds typically had masses between 1 million and 1 billion solar masses, far larger than today's stars. Their interiors consisted almost entirely of hydrogen and helium, with extremely low density and very low temperature, only about 10 Kelvin, colder than today's interstellar space. But even under these conditions, gravity continued its relentless work. The central regions of gas clouds began contracting, with density and temperature slowly rising. Unlike modern star formation, this process lacked the assistance of heavy elements. In modern star-forming regions, heavy elements act as coolants, helping gas clouds radiate away heat and contract more easily. But in the early universe, only atomic transitions of hydrogen and helium could provide limited cooling. This lack of cooling meant early gas clouds found it difficult to fragment into smaller pieces. In today's star-forming regions, a large molecular cloud will fragment into thousands of smaller cores, each eventually forming a star with mass comparable to the Sun. But in the early universe, entire gas clouds often contracted as a whole, forming extremely massive stars. When the gas cloud's central temperature reached about 1000 Kelvin, hydrogen molecules began forming in large quantities. This was a critical turning point because hydrogen molecules are effective coolants. Molecular vibrational and rotational energy levels can absorb thermal energy and radiate it away to space as infrared radiation. With hydrogen molecules' help, the gas cloud's contraction rate began accelerating. But the hydrogen molecule formation process itself was full of drama. Under early universe conditions, hydrogen molecule formation required a complex chemical reaction network. First, cosmic rays or other high-energy processes had to ionize some hydrogen atoms, producing free electrons. Then these electrons combined with hydrogen atoms to form negative hydrogen ions. Finally, negative hydrogen ions combined with another hydrogen atom, releasing an electron and forming hydrogen molecules. This process was extremely fragile. If cosmic ray intensity differed slightly, if gas density varied slightly, hydrogen molecule formation efficiency would be greatly reduced. More dangerously, ultraviolet radiation could easily dissociate hydrogen molecules. In the early stages of star formation, if any ultraviolet sources existed, the entire process could halt. However, in certain fortunate regions, all conditions were just right. Gas clouds continued contracting, central temperature continued rising. When temperature reached several thousand Kelvin, hydrogen atoms began ionizing, and gas became plasma again. At this point, hydrogen molecule cooling became ineffective, but gravity was already strong enough to maintain the contraction process. When central temperature approached 10 million Kelvin, hydrogen nuclear fusion finally ignited. This marked the birth of the universe's first star. But this star was completely different from any star we see today. Due to the lack of heavy elements, its mass was extremely large, possibly 100 to 1000 times the Sun's mass. Its surface temperature exceeded 100,000 Kelvin, 20 times hotter than the Sun's surface. Its luminosity might have been 1,000,000 times that of the Sun. These first-generation stars, called population 3 stars by astrophysicists, were truly cosmic monsters. Their core temperatures far exceeded modern stars, and nuclear fusion reactions proceeded extremely violently. In their interiors, hydrogen was rapidly converted to helium, helium further fused into carbon, nitrogen, oxygen. As nuclear fusion progressed, increasingly heavy elements were produced in stellar cores: neon, magnesium, silicon, sulfur, and finally iron. But it was precisely this extreme nature that determined population 3 stars' fate. Such massive size meant they consumed nuclear fuel extremely rapidly. Modern Sun can burn stably for 10 billion years, but population 3 stars' lifespans might be only a few million years. They were like cosmic fireworks, burning briefly and brilliantly, then quickly heading toward death. When population 3 stars exhausted their nuclear fuel, they faced catastrophic endings. Their enormous mass made it impossible for them to die gently like smaller stars. Instead, their cores would rapidly collapse under gravity, triggering a supernova explosion, or more accurately, a hypernova explosion. This explosion's energy was 10 to 100 times that of ordinary supernovae, enough to illuminate half the universe. But hypernovae's significance went far beyond their brightness. During the explosion process, heavy elements produced in stellar interiors were ejected into surrounding interstellar space. Carbon, oxygen, silicon, iron, all these basic elements that constitute planets and life, appeared in the universe for the first time. In a sense, population 3 stars' deaths provided necessary raw materials for subsequent stellar and planetary systems. The dispersal process of these heavy elements was itself a spectacular sight. Shock waves from supernova explosions propagated outward at thousands of kilometers per second, sweeping through surrounding gas clouds. Under shock wave action, originally sparse hydrogen-helium gas was heated, compressed, and mixed with heavy elements. This process not only changed the gas's chemical composition but also triggered new rounds of star formation. With heavy elements present, second-generation star formation processes were completely different from the first generation. Heavy elements provided more effective cooling mechanisms, allowing gas clouds to contract and fragment more easily. This meant second-generation stars typically had much smaller masses than the first generation and much longer lifespans. More importantly, heavy elements' presence made planet formation possible. But population 3 stars' legacy was not just heavy elements. Their intense ultraviolet radiation began ionizing surrounding neutral hydrogen gas, creating enormous ionization bubbles. As more and more population 3 stars were born and died, these ionization bubbles began overlapping and merging. Eventually, the entire universe became ionized again. This process is called reionization. Reionization marked the end of the cosmic dark ages. Although population 3 stars themselves might not be directly observable by us, they are too distant, too ancient, their influence can still be detected today. Certain features of the cosmic microwave background radiation, the ionization state of the interstellar medium, even the properties of the most distant galaxies we observe today, all carry evidence of population 3 stars' existence. However, regarding population 3 stars, we still have too many unsolved mysteries. What was their exact mass range? How were they distributed? What percentage of population 3 stars formed black holes rather than undergoing supernova explosions? The answers to these questions will determine our understanding of the early universe. Deeper mysteries involve population 3 stars' influence on subsequent cosmic evolution. If population 3 stars were more massive, they would produce fewer heavy elements, making subsequent star and planet formation more difficult. If they were fewer in number, cosmic reionization would be delayed, and second-generation star formation would also be postponed. In a sense, population 3 stars' properties determined the entire universe's evolutionary trajectory. Even more puzzling is the relationship between population 3 stars and dark matter. We know dark matter played a key role in early structure formation, but how did dark matter halo mass and distribution affect population 3 star formation? Do certain dark matter halos exist that were too small or too large to form population 3 stars? These questions involve our understanding of dark matter's nature, which remains a major mystery in modern physics. Another profound question is population 3 stars' diversity. Although we typically discuss population 3 stars as a whole, in reality, population 3 stars formed with different masses and in different environments might have had completely different properties and fates. Some might have formed the first black holes, becoming seeds for later supermassive black holes. Others might have experienced pulsational instability, ejecting large amounts of matter without complete destruction. Still others might have formed exotic objects like quark stars or magnetars. An important consequence of this diversity is the uneven distribution of heavy elements. Different types of population 3 stars would produce different heavy element combinations. Some stars might be rich in oxygen and magnesium, others might be rich in silicon and iron. This chemical inhomogeneity would affect subsequent star formation and evolution, creating stellar populations with different chemical compositions. Even more fascinating is population 3 stars' possible influence on life's origins. Although population 3 stars themselves could not possibly have planetary systems suitable for life, the heavy elements they produced laid the foundation for subsequent life's emergence. Moreover, population 3 stars' radiation and explosions might have created complex chemical environments where some early chemical evolution processes might have occurred. From a philosophical perspective, population 3 stars' existence raises a profound question: does the universe necessarily produce complexity and life? If population 3 stars had not formed, or if their properties had been slightly different, subsequent cosmic evolution would have been completely different. Our existence depends on these ancient stars' precise properties, which makes one wonder: is this accidental or inevitable? Furthermore, population 3 star research reveals a fundamental characteristic of cosmic evolution: increasing complexity. From the initial hydrogen and helium, to heavy elements produced by population 3 stars, to planets and life formed in subsequent stellar systems, the universe seems to have an inherent tendency to continuously create more complex structures. But will this tendency continue infinitely? In the distant future, when all stars have burned out, when the universe becomes cold and sparse, can complexity continue growing? These questions bring us to a grander perspective. Population 3 stars are not just a chapter in cosmic history, they are the crucial bridge connecting the universe's birth to our present. Without them, there would be no heavy elements; without heavy elements, there would be no planets; without planets, there would be no life. In this sense, each of us is a descendant of population 3 stars, a legacy left by those ancient giants. When we review this history from the Big Bang to the first stars, we see not just a series of physical processes, but an epic of creation. In that moment 13.8 billion years ago, the universe went from nothing to something, from simple to complex, from chaos to order. Each stage laid the foundation for the next, each process created possibilities for subsequent developments. The Big Bang created time and space, inflation determined the universe's geometric structure, nucleosynthesis produced light elements, recombination released the first light, density fluctuations sowed the seeds of structure formation, and population 3 stars produced heavy elements and reionized the universe. This was a perfectly coordinated process where any minor change in any link could have led to completely different results. But perhaps most amazing is that we can actually understand all this. We use mathematical equations to describe the Big Bang's physical processes, use telescopes to observe distant galaxies to study the universe's early state, use computer simulations to recreate population 3 star formation processes. We are not only products of cosmic evolution but also tools for the universe to know itself. This cognitive ability itself raises profound questions. Why is the universe's structure precisely such that it allows intelligent life to emerge? Why are physical laws so precisely tuned that every step from the Big Bang to population 3 stars could proceed smoothly? Is this accidental coincidence, or does some deeper principle exist? Some scientists have proposed the concept of the anthropic principle, the universe's properties we observe must be compatible with our existence, otherwise we would not be here asking these questions. But this explanation, while logically sound, somewhat evades deeper questions. Why would there be a universe that allows observers to exist? Why do physical laws have this form? Other scientists have proposed the concept of a multiverse. Perhaps countless universes exist, each with different physical constants and initial conditions. We find ourselves in such a life-friendly universe merely because no observers would exist in unsuitable universes. But this theory, while elegant, is almost impossible to verify. Whatever the ultimate answer, the history from the Big Bang to population 3 stars reveals a fundamental characteristic of the universe. It is a system that continuously creates novel things. From initial quantum fluctuations to complex stellar systems, from simple hydrogen atoms to complex life molecules, the universe seems to have an inherent creativity, continuously breaking through existing boundaries and exploring new possibilities. This creativity reached an important milestone in population 3 star formation. These stars were not merely aggregations of hydrogen and helium, they were the universe's first attempt at creating complexity. In their cores, simple hydrogen nuclei were transformed into complex heavy elements. In their depths, these heavy elements were scattered throughout the universe, providing raw materials for subsequent, more complex structures. In a sense, population 3 stars were the universe's alchemists, transforming simple elements into complex elements, chaos into order, possibility into reality. Their existence proves that the universe is not merely a mechanical, predictable system, but a laboratory full of creativity and possibilities. When we look up at the starry sky tonight, every star we see carries traces of this ancient history. The heavy elements in those stars come from population 3 star interiors. The rocks and metals on those planets come from population 3 star explosions. Even the carbon, oxygen, and iron in our bodies were once formed in population 3 star cores. We are not merely observers of the universe, we are living evidence of cosmic history. Our existence proves that the Big Bang indeed occurred, proves that population 3 stars indeed existed, proves that evolution from simple to complex is indeed possible. We are the latest product of 13.8 billion years of cosmic evolution, and possibly the highest form of the universe knowing itself. But this realization also brings responsibility. If we truly are tools for the universe's self-knowledge, then we have an obligation to continue exploring, continue understanding, continue pushing the boundaries of knowledge. We must not only answer the question, how did the universe begin, but also answer deeper questions like, how will the universe end, and, what role do we play in it? The history from the Big Bang to population 3 stars tells us that the universe is a continuously changing, continuously creating system. It began from the simplest state and, through a series of precisely coordinated processes, created increasingly complex structures. This process continues, and we are part of this process. Perhaps the most awe-inspiring realization is that all this originated from that moment 13.8 billion years ago. In that point smaller than an atomic nucleus was contained everything that would later emerge, all galaxies, all stars, all planets, all life, all thoughts. In a sense, our existence today, our understanding of the universe, even our ability to contemplate these questions, are all direct consequences of that initial moment. This is the universe's greatest gift to us, not just existence, but the ability to understand existence. We can not only experience this universe but also understand how it formed, our place within it, and its possible future. This understanding ability itself is a miracle of cosmic evolution, the ultimate achievement of that magnificent journey from the Big Bang to population 3 stars.